All right, surprisingly, this 2000 question is one of the only ones that was non-calculator active for story problems. And it's very important because these are the ones that we've kind of done similarly in class. It's been a while that kind of go in and out. Something's coming in and something's coming out. So this is a great one to start because it's non-calculator active, which your AP exam, a lot of it is non-calculator active. And then we can get to the ones on just setting them up, right? Because they're calculator active. So let's go ahead and get rolling. So water is pumped into an underground tank at a constant rate of 8 gallons per minute. This is telling you the derivative, technically, right? The speed. And that's telling you that water is being pumped at a constant rate of 8. I'm gonna write 8T because it's it's 8 gallons per minute, T representing minutes. So we got something coming in. Water leaks out of the tank at a rate modeled by this function, gallons per minute, from 0 to 120 minutes. So now we know that there is something, right, coming out right here, given by this function, T plus 1. And then it says at T equals 0, the tank contains 30 gallons of water. So as of right now in here, there is 30 gallons of water. So you can see something's coming in, something's coming out, and we have some initial condition. And all these are important to take into account because each question is going to ask something specifically about that. So let's go ahead and go to part A here and think about what part A is asking us. How many gallons of water leak out of the tank from T equals 0 to T equals 3 minutes? So they're saying how many gallons of water leak out of the tank. Does it ask you how much is there? No. Is it asking you how much went in? No. They're asking you how much went out. All they care about is the green stuff that I just drew. All they want to know is how much got out of the tank. Well, if I write PVA up in this corner, everything that we were given to us was technically our velocity function. And what we got to do is we got to go backwards because it's asking for gallons, right? Take a look at the units. Gallons per minute, gallons. We're going backwards. So what I need to do is take the antiderivative of this from 0 to 3 of the square root, zoom, T plus 1, and then dt right here. So we need to take the antiderivative of this in order for us to figure out how much gallons leaked out of the tank. I do not need to put 30 plus because that would tell me how much is remaining after it leaked out, not including what went in. So we don't care about anything of how much we started with. We just care about how much actually got leaked out. That's why we do not need the initial condition. So let's go ahead and do this. I'm going to rewrite it like this though real quick. So I'm going to write this like this, okay? Now, when I write it like this, I wrote this as t to the 1/2 because it's a square root function. We're going to take the antiderivative of this. Well, that means I need to add by 1 to the exponent and then divide because it's the antiderivative. So I'm going to get t plus 1. And this is going to be raised to the power of 3 over 2. Really important that we know, right? Just to refresh our memories, it's adding because it's the anti. And then we're going to divide by that new power. So this is divided by 3 over 2. Okay, I'll put a little time symbol real quick because we're going to take the derivative of the inside. You always have to do that. Well, what's the derivative of t? The derivative of t is 1, so then we divide by 1. So I'm not going to put that there, but just keep that in mind because, that's going to potentially show up. Okay, now we're going to raise the 2 up here. So then we're going to get this. So all we did now is just bring the 2 up. Once you bring the 2 up, you rewrite everything the same. We put this little line. I personally like to put a set of parentheses, right? That way you don't forget it. You want to do that for every problem. This one you don't have to because you don't have like separate functions in between them. But nonetheless, from 0 to 3. So now let's go ahead and take our 3, plug it in, our 0, and let's solve this out. So I'm going to do this over here in this corner. Give me a moment. I'm just going to write it all out first, and then we'll talk about it. Okay, if you take a look over here, one thing for you to know is I plugged in the 3 for the t. 3 plus 1 is 4. That's why this is a 4 inside here. And then we got this expression subtracted by, I took my 0 and I plug it in for the t. Well, 0 plus 1 is 1. So that goes right there. So far, this is what I have. And I need to simplify this out. Remember, it's subtract always. Well, how do I do this right here? Well, I'm going to put this in the corner. 4 raised to the power of 3 over 2. Whenever you have a fractional exponent, remember the bottom part means square root. So if this was like a 4, it's like, or 3, it'd be cubic. If it was a 4, it'd be quartic. So one number multiplies by itself twice to give me 4. Well, what's the square root of 4? That's 2. We get 2 to the power of 3 because we didn't do anything with the 3 yet. 2 to the power of 3 is 8, okay? So if I go over here, I'm going to get 2 times 8 right here. So I'm going to write 2 times 8. That was a really bad 8, by the way. Divided by 3. Subtracted by 2 over 3. Now, why do I know this is 2 over 3? Well, 1 raised to any power is 1. 1, the square root of 1 is 1. 1 to the third power is 1. So 2 times 8 is 16. I get 16 over 3 minus 2 over 3. And then last but not least, putting this all together, I'm going to get 14 over 3 gallons. There it is. So I'm going to go ahead and write gallons because we did the antiderivative. So how many gallons of water leaked out the tank? Well, 14 over 3 gallons is what leaked out of the tank for this problem. So hopefully that makes sense for part A. We're going to go ahead and go on to part B. All right, let's go ahead and go on to part B. Now, part B is kind of like the bread and butter of these in and out stories, and they're really, really tough at first. How many gallons of water? So if I write PVA, we already know we got to go to position, are in the tank. They're asking you how many gallons of water are there. So just to kind of redraw our diagram one last time, that means we need to take into account everything, right? We need to count how much is there to start with, how much went in, and how much went out. And we take all of that to account, and that's going to tell us exactly how much actual gallons of water are in the tank after 3 minutes. So we need to take into account how much went in, how much went out, and what was our starting. So you guys know, I personally like to do, right? I like to do my starting. So I'll write starting. I like to do my starting plus my in minus my out. I think that's just a natural progression. How much did we start with? How much got added in? And then how much got out? So we know at t equals 0, the tank contains 30 gallons of water. So I'm going to come over here. And this is what I'm going to write so far. I'm going to write 30. That is my starting value. Plus, well, how much is going in? Well, what is going in is water is pumped into an underground tank at a constant rate of 8 gallons per minute, right? If you remember, I wrote that before. That's 8T. Right, so it's 8 gallon per minute, AT, constant rate. So plus AT, like this, minus, well, we need to figure out, by the way, hold on real quick. And obviously we're gonna need to plug in 3 for the T later to tell us how many gallons went in, right? It's at a constant rate. So, you know, if you want to, you could do the antiderivative of this, but technically we can just plug it in, we can just technically plug in our value into this, okay? Subtracted by how much went out. Well, how much went out is over here. Now this gave us rates, and it's a function. It's a function, so we need to take the antiderivative of that. 3 goes on the top because 3 minutes. Well, 0 on the bottom. We got the initial condition right here, and then again, this is going to be from t plus 1 to the 1/2 dt. Now here's the beautiful part. By part A, we technically already did this. We already know this is 14 over 3 gallons. So this is what we need to do then. 30 plus 8 times 3, right? This is going to tell me how much gallons got put into the tank. And I want you to keep in mind, it's at a constant rate of 8. That's why I wrote AT. If I really wanted to, if like I was to go to the very core of antiderivatives, I don't want to confuse you. Technically, you would do 30 plus the antiderivative of 8 dt because it's just constant from 0 to 3. But then when you take the antiderivative of this, you're going to get AT. And I mean, that's basically the same thing. That's why I just did AT. That's like, this right here is like your original function, right? It's kind of 8 times the time. I don't know, constant functions, that means linear. So that just lets me know what it is as long as I'm aware. And last but not least, when I plug in the 3, the 8 is gallons per minute, the 3 is minutes, the minutes cancel, and then I'm given the gallons. So minus 14 over 3. 8 times 3 is 24. 24 plus 30 is 54. Minus 14 over 3 gallons. Okay, that's, I could write it like this if I want to, or I could multiply by 3 up in both and get the actual value. But this is really my final solution here. And obviously you don't want to box anything on the AP exam. I'm just showing you right there, okay? So constant rates, again, the original is just AT because how many gallons are going to be added? You plug in the 3, that's, you know, 24 gallons that's going to be added, right? I don't need to do anything fancy here. But if you wanted to, you could have technically done this right here. This would have represented 8 is constant, and then you take the antiderivative, and that's how you get the AT. So hopefully that makes sense. Just wanted to show you two different ways of going about it. With that being said, let's go on to part C. So part C is actually almost identical to part B. Write an expression for A of t, the total number of gallons of water in the tank at time t. It's basically saying make a formula that will allow you to solve this. Instead of 3 minutes, it's 10 minutes, 5 minutes, 12 minutes. So really this is just saying make an equation that represents that. Well, we kind of already had one. We have A of t. We had our starting plus what is going to go in. Bam. Subtracted by what's going to go out. 0. This is the square root of t plus 1 dt. And really up here, this is what usually would be the value that we're looking for. In this case, they just wanted t. So then we just write the t up here and we're done. This is technically it. That's all you had to do. Just make an equation that would help you find that. Or, just so you know, again, totally up to you. You can write this as 30 plus the antiderivative from 0 to t of 8 dt. Right? Because this is the constant 8. You don't have to, if you get confused by this, you could do it like this, subtracted by antiderivative from 0 to t, and then we get our square root function, t plus 1 right here, dt. So really, if you want to, you can write it as both. I prefer the at because it's just constant, so I know it's at, but nonetheless, you can do it this way as well. All right, let's go ahead and move on to part D, which is a pretty good one. Part D is a little bit tougher, okay? It says at what time t from 0 to 120 is the amount of water in the tank a maximum. That is technically like asking you for an absolute maximum, right? Because it's asking you from 0 to 120, when is the amount of water in the tank a max? And that's a lot of work that can be involved here. Now, we already know at 0, it's 30 gallons to start off with, right? So there's two ways to go about this, right? This is kind of one way right here. We're gonna get 0. Let me go ahead and write it out. 0. Remember, we're going to check our endpoints. 120. This is 30 right here. Now, this is a little bit of a bummer because this is non-calculator active. So having to do 120 is a lot of work. So there's kind of like another way that we can kind of think about this, okay? And that's this right here. We want to find when the water is at a maximum. Well, we know water's coming in and water's coming out, right? Originally, if I wrote PVA, they gave us our derivative. So I could really write for our derivative function, we'll say a prime of t because they told us a of t, so we'll write a prime of t. Now we know that water is coming in at a constant rate of 8. Now I'm not going to write at because that was the original function, just 8 minus the square root of t plus 1. And as water goes in, water's coming out, right? We kind of know that to be true. And we want to find when these balance each other out, when this is equal to 0. And I'll tell you why in a moment. When the rate of this going in and the rate of this going out are the same, that's 0, right? And now we know there's going to be some change in between them, and I'll tell you what I mean by that. So we're going to set this equal to 0 and we're going to solve it. I'm personally going to add the square root of t plus 1 to both sides, and we're going to get 8 is equal to the square root of t plus 1 right here. And then what I'm going to do is we're going to square both sides, right? So that we can get rid of the square root symbol. That's going to give me 64. It's going to equal t plus 1 because these cancel. Subtract 1 to both sides. And we get t is equal to 63. So now we know that 63 is 63 minutes, right? The rate are equal to each other. Rate was coming in, rate was coming out. That's when they're officially equal to each other. Now, is it a maximum or a minimum? Well, we're going to do a line test. We're going to write 63 min. We're going to put, 0. We already had 0. We already knew at 0, it contains 30 gallons of water, but also we need to know what the rate is, correct? So if we go about doing this, we already know rate-wise, if I plug in 0 into my rate function up here, okay, I get 0 plus 1, that's 1. 8 minus 1 is a positive, so I get positive. Remember, I'm plugging this into my derivative function, so I can see whether it goes from relative min or max. Then I'm going to plug in a bigger number, like 100 or 120, right? And if I plug in 120 plus 1, the square root of that, well, I need to think for a moment. The square root of 100 is 10. So I already know now anything above 100, 8 minus that will be negative. And if I look right here, I can already tell that right here, this is a maximum, right? That's going to tell us right here that this is a maximum. And this is good to know. That means everything leading up to this is increasing. That means more water is entering than leaking out, okay? And then it's decreasing, right? More water is coming out at this section here. So this derivative function tells us a lot. This tells us that this has to be the time that the water is at a maximum, because this was increasing throughout, right? We started with 30 gallons. It's increasing, we reach up here, and then it's decreasing. So you know for a fact it can't be at a maximum because it's going down. So that's how this relative min or max is very helpful, because now I know at t equals to 63 minutes, it is at a maximum because a prime of t changes signs from positive to negative at 63. So hopefully that makes sense. This was a little bit of a tough one.